try again. Okay, now I've got it hooked up to my camera. Can anybody hear me now? Yay. Okay, I make no promises on this camera. It's got a loose connection and it might cut out at any moment. I'll keep trying to look for it. Okay, so a lot of times when we did partial fraction decompositions, we came up with an integral that looked something like this. And so is that an easy integral for you? What is it?
2 natural log of absolute value x minus 3.
That's right. What if, instead of what we have there, what if we had something like this? What difference does putting a coefficient in front of the x do? You can, but this is not a factor of 5. What does it do to this part here other than putting it here? What else happens?
Divided by the derivative.
Yeah, you get a 5 out here, right? Because if I had a 5 there, we would take u to be 5x minus 3. So du would give us a 5 times the dx. So that's where we get the 1/5 out front. But the one we had just had a coefficient of 1, so that's why I didn't have that 5 there. So keep a lookout. If you've got a first degree term down here, look out for coefficients. Okay? Then, not everything with a denominator makes a logarithm. In number 2, we've got the same first term. So those are all different. They can't possibly all be logarithms if they're all different from one another. So what you think of is what these look like if we did make the Udu substitution, where u is x minus 3 and du is dx. Then we could write this as a 1 over u integral, but we would write this as a 1 over u squared integral. Those we move upstairs and write as u to the negative 2 and use the power rule. Same deal here. So if I do that substitution where u is x minus 3, I can write this as 2 times the integral of 1 over u plus 5 times the integral of u to the negative 2 minus the integral of u to the negative 3. And my glare is fierce. So the first one's a logarithm. Now when we use the power rule, you add 1 to the power and divide by the new power. So the middle one becomes u to the negative 1 over negative 1. The one on the end becomes u to the negative 2 divided by negative 2. So we would have 2 times the natural log of u, but u is x minus 3, plus 5. This is going to be u to the negative 1 over negative 1, so we put the negative 1 here. And our u is x minus 3. And then minus, this becomes u to the minus 2 divided by a negative 2. So I changed the sign there. And if you want those x minus 3's to a negative power, it can be written in the denominator. So I can put one more line here and write that as 2 times the natural log of the absolute value of x minus 3 minus 5 over x minus 3 to the first power plus 1 over 2 times x minus 3 squared. Which one? This one? The 2 is going to be on the bottom because the 2 comes from dividing by the new power.
Oh,
So when you divide by the new power, it gives you a -2, but I changed the sign, made that a +2. So the 2 will definitely be on the bottom. Okay? All right, let's look at the next one. I don't need much room for the next one. The next one's the integral of 5 divided by the square root of 4 minus x squared.
You skipped number 3.
I skipped number 3 because that's the wrong paper. Let's go to my phone. Let me go to number 3. Got so many different versions of this handout. Okay, so number 3. Number 3 is short too, so let's just rub that out and put a 4 up there. I'll go over here and put aside number 3. We've got a cosine squared times the sine of x as our number 3. Anything jump out at you?
UDU?
UDU. I've got a cosine and I've got its derivative. Right? All the action's going on to the cosine. So we'll take u to be the cosine of x, and its derivative is the sine of x. So always look for UDU first. This derivative is going to give us a minus sine of x. So I can put the minus with the du. And we're just integrating minus u squared du. So add 1 to the power, divide by the new power. We get a minus u cubed over 3. Where u is the cosine of x. Okay? What if I had cosine squared times sine squared? Put power on the sine, put an even power on the sine, put a 2 up here, and it's no longer a UDU integral, nor do we have the option of a UDU integral. What do you do when both powers on sine and cosine are even?
You change it into the 1 minus sine squared.
Now, not the 1 minus sine squared. We don't want to keep, because you'll still have even powers, right? To get rid of the even powers, if both are even, we use the power reduction formula. The cosine squared has a trig identity of 1 plus the cosine of 2 times the variable divided by 2, and the sine is 1 minus 2 times the variable. So for even powers on sine and cosine, you do the power reduction formulas. But if one of them is odd, you do a UDU. Okay? All right, there's the next one, and it only needs that much room. So look over there at number 4. Tell me what you know or don't know about number 4.
Or plus.
Is it a plus? Well, son of a biscuit.
Does that make it harder?
Yep, it does, because what do you know about the one with the minus? What if it had the minus? So this is my number 4. Let's just call this an extra problem. No extra charge to get the extra problem. What do you know about that one?
Can we do a trig substitution?
You don't even need a trig substitution. It's already a known integral. That's a known integral for you. Which one is it? It's the arc sine. The integral of 1 over a squared minus x squared dx is an arc sine of x divided by a. So this one already has the right format. This one has the 5 out front. Our a is going to be a 2. So it's the arc sine of x divided by 2. But you told me the one on our handout has a plus. That's totally different. If I'd had the plus without the square root sign, then it's an inverse tangent. So if we had the integral of 5 over 4 plus x squared dx, that's another known integral. The integral of 1 over a squared plus x squared is an inverse tangent. And that one has a 1 over a out front, and the arc tangent of x over a right here. So in this case, we would have 5 times 1/2 the arc tangent of x over 2. So that's a known integral. With the square root sign, it's no longer a known integral. So I agree, with the square root sign, we look for u du, but we only have a 5 on top, so it's not a u du integral. So we will have to do some version of a trig substitution. So let me give you a few minutes to do it while I put the problem up here. So here's our handout problem number 4. 5 over the square root of x squared plus 4. Quiz yourself. See if you can do this without looking at the stuff that you did before. If you need to peek, I guess it'll be okay. See if you know the right trig substitution to make to help you get rid of the radical sign. Off the light up front. That's worse for y'all, isn't it? Yeah, that's no better. Who wants to tell us what the substitution is going to be? Tangent. Take x to be 2 tangent of theta. Don't forget your dx term. Make sure everybody gets the right start. We're taking x to be 2 tangent of theta. Don't forget the dx. And eventually we're going to use the identity that tangent squared plus 1 is equal to secant squared. That's our goal. That's our motivation. I think I can take this mask today. Okay. About the formula? All right, let me remind you of the formula. Move all of these over. We got the arc sine formula, we got the arc tangent formula. Might use that. Does that simplify to an interval of a secant? Anybody? Yes? And the integral of secant is the natural log of the secant plus the tangent. Kind of easy to remember because the derivative of a secant is the product of secant tangent. The integral just has the plus sign and the logarithm. So let's see, the derivative of 2 tangent theta was 2 secant squared theta. So when we put that in there, I can go ahead and pull the 5 way out front. In its place, I'm going to put the 2 secant squared theta d theta. In the radical sign, I'm going to square this. I'm going to have a 4 tangent squared theta. And I've got the plus 4 here and the radical sign. And it is the common factor of 4 that we pull out, and what remains is our tangent squared theta plus 1. It's still under the radical sign. And here's where that identity comes in handy. The tangent squared theta plus 1 is secant squared. So I have 4 secant squared of theta multiplied together under the radical sign. Now I'm able to take the square root of each term. So I'm going to get a 2 secant of theta in the denominator. So everything cancels, leaving me with just the integral of the secant of theta. And that's where we pull out our formula that we know. Natural log of secant of theta plus the tangent of theta. So we got to go back and get this in terms of x. So we move back over here and write that the tangent of theta is x over 2. So we can figure out the secant of theta. Tangent is opposite over adjacent. This squared plus that squared is the hypotenuse squared. So the hypotenuse is going to be the 4 plus x squared. I need the hypotenuse because the secant is hypotenuse over adjacent. So we can write this now as the natural log of the square root of 4 plus x squared over 2. And then the tangent was x over 2. Yes, sir.
Would your 5 go on the outside?
And the 5 is right here, and I knew I'd lose it, and I told myself not to lose it, and I lost it anyway. Thank you for finding it. There's a 5 out front there. Were you able to get all the way to the end before I interrupted you? All right, let me see what's next. Okay, so let's kind of look at problems 5 and 6 together. Number 5 is the integral of x times e to the 2x. And number 6 is the integral, come on back, x e to the x squared. Neither of them is very hard, but one of them is easier than the other. Which one's the easier one?
Is number 6 easy?
Sorry?
Number 6?
I think it's the second one. Why do I think the second one's easier than the first one?
It's got the x squared and then the derivative of the bottom.
That's right. Always look for u du. The power has its derivative right here. So this one's just an ordinary u du integral. But if I tried that here, take u to be the power, du is a constant. So I don't have anything for this. So this is not a u du integral, that one is. So do that one first. Do number 6 first. Because this is an x squared, this is a u du integral. All right, so it's got 2 steps. u is x squared, du is 2x dx. So I'm going to put half du in for x dx. So we get the 1/2 right here. And this is now an integral of e to the u du. And the integral of e to the u is e to the u, where u is x squared. Okay? All right, so if it's not a u du integral, what do you want to try on number 5? Say again?
Integration by parts.
Integration by parts. So let's do that. Try integration by parts. I'm going to give you a minute to try it. I'm going to write this as u v minus the integral of v du. Given the choice, the u part is usually the polynomial. Right? When you're not given the choice of when the integral contains a logarithm or an inverse trig, because you don't know the integrals of those. Given a choice, u is the polynomial and dv is the more complicated looking part. So in this example, u is going to be x, dv is e to the 2x. So that the derivative of u is just dx. What do you get when you integrate e to the 2x? That's right, just like when you have that extra constant on your 1/u integral. This is going to come out as a 1/2. So we want to make sure that this integral is easier than that one. So let's try it. The u times v is x times 1/2 e to the 2x. I'll just write that as x over 2 e to the 2x. And then v times du is easier because replacing the x is now just the 1/2. Constants don't make things harder. Constants make things easier. So now this is lower degree than what we started with. So this is going to work. Now we just integrate this and get another 1/2 e to the 2x. Multiply that, gives me a 4th out in front. So x over 2 e to the 2x minus 1/4 e to the 2x plus c. Okay? This will always be the x unless your integral contains a logarithm or an inverse trig function right here. Then you have to swap it. All right, number 7. Integral of sine squared of 3x. Was that number 6? That's number 7? Have you seen an integral of sine squared anywhere? Yeah, that's one we did over and over and over again in chapter 6. What's the formula for the integral of the sine squared of a variable, theta?
Theta over 2 minus sine of 2 theta over 4.
So that's a known integral. The integral of sine squared of theta is theta over 2 minus the sine of 2 theta over 4. What's going to happen with that 3 that I got stuck in there next to the theta? You do a substitution, right? Do a substitution, make this a sine squared of u. And see what happens with that extra 3 that you get. U is going to be 3x. du is 3 times dx. So 1/3 du is dx. And this integral becomes 1/3, I said, integral sine squared of u du. And so we should get u divided by 2 minus the sine of 2u divided by 4. With the 1/3 out front. And then replace each u with 3x. So 2 times 3x is going to give me a sine of 6x right here. Okay. We can also use a trig identity for when we do the trig substitution integrals, that we can rewrite the sine of 2 times theta is 2 sine theta cosine theta. So another way to remember this formula is theta over 2 minus 2 sine theta cosine theta over 4. The 2's will cancel, and then you would just have theta minus sine theta cosine theta all over 2, if that's easier for you to remember. It'll be easier for us to use when we're doing those trig substitution integrals to get the expression back in terms of x. next one. We have 3 divided by x squared plus 4x. Do you agree that it's not a UDU integral? It's also slightly off from being the inverse tangent. That x keeps us away from the inverse tangent integral. So there's a couple of things you can try here. Let me see what you choose to try. Again? Do the partial fractions decomposition. I think will work for you. Try the partial fractions. You can write this fraction in terms of the sum of simpler fractions. See if you can find 2 fractions that add to this one. Because if you give me some idea of how long it takes you to do these, then I need to know how many of these put on the test for you. 1, get it or don't get it. Right? I wonder if I can make up a problem that has all these techniques in one. You do a trig substitution to get something that's a partial fraction.
Do like 10 problems, just all split up.
All split up. You can do that. When I was in graduate school, I had this stats class, and there would be essentially one problem on the test, but it had parts A through Q. And me, I would mess up on part B, so I hadn't had a chance in Helsinki of being part Q.
Hey guys, we're doing a 2-question test today. Parts A to Z.
That's right. I was so mad at that. I begin to tell you how much I hated graduate school.
Did you expect to like it?
I know. What was I thinking? Well, as an undergraduate, college was fun. I thought, well, I'll just do some more of this. Oh, gosh. I don't tell you that in graduate school. It's just a hero fly. What, 27 days? We got at the halfway point. Pretty interesting. Nice whole numbers, or? No, fractions are okay. Uh-oh, you got 8 to 0. That's not good. Uh-oh. Numbers 4. No. So how did you put in the coefficients? Constant. So you should have the constant. Here's a frame. Where is it? There you go. Found it. You get 3/4-ish for each of them. One's positive, one's negative. Good. No? Yep. Okay. Right, let me catch up with you. Those are linear factors. So we guess constants over each of our fractions. Each factor is on the bottom. And then cross multiply so that you get the equation 3 is equal to A times x plus 4 plus B times x. If you let x equal 0, you'll get A. The because that'll be 0. This will be 4a is equal to 3. So a is 3/4. If you let x equal -4, you'll get b. Over here, you'll have 3. That'll be 0, but I'll have b times -4. So b is a -3/4. And then we're left integrating this as a positive 3/4 over x. And then a -3/4 over x plus 4. Those are both first degree factors with a coefficient of 1. So we've seen that they're both going to be logarithms. We get 3/4 natural log of x minus 3/4 natural log of x plus 4. Okay, our next one. Two x times the cosine of 3x. Is it a UDU integral? Not a UDU integral, so how are you going to do it? Integration by parts. Integration by parts. Polynomial times a trig. All right, let's make sure you don't lose any of your constants. All right, let's see if that's enough time here. Again, given the choice, take the u to be the polynomial part and the dv to be the trig part. So the du this time is going to be a 2 times dx. What is that little 3 inside here going to do when I take my antiderivative? Divide. So give me a 1/3 out front. The integral of the cosine is a positive sign. And so now we do uv minus the integral of v du. So u times v gives me a 2x over 3 times the sine of 3x minus the integral of v times du. So I'll put a 2/3 here, sine of 3x dx. So we do have an easier second integral. It's gone down by a degree, so now we can just integrate the sine. This is going to give us another factor of a third, and the integral of the sine is a negative cosine. So it's going to give me a plus here. So we'll get 2x over 3, sine of 3x. So that's going to change the sign to plus. Another factor of 3 gives me a 2/9. That's a cosine of 3x. And now we're done. So how are you doing keeping up with all your coefficients? Yes, ma'am?
Why is it usually to go like to find the I have it as 1/3?
Because I've got a derivative here giving me a 2.
Oh,
Did you lose the 2? That's why I put them in there. When we first learned this, I left all the coefficients out. Now I'm putting them in there. See if you're paying attention to detail and getting all your little numbers everywhere. I lose them too, but I'm not getting a grade in the class, so. Fair enough. Work hard and pay attention to all your little goofy numbers. Okay, the next one, number 10. You're going to ask yourself, known integral, UDU integral? Is it one of my easy ones? Is it a known integral? Is it a UDU integral? It's neither, right? I got an x squared under a radical. I don't have an x outside the radical. So it's not a UDU. It's not a known integral. What do you want to do? You can do a trig sub. What's our trig sub when the variable is behind the minus sign? It's a sign, because we're going to try to eventually use the identity that 1 minus sine squared is cosine squared. Does it bother you that the 5 is not a perfect square?
Yes.
Get over it. So what are you going to do? X is equal to what times sine of theta? Square root of 5. X is equal to the square root of 5 times the sine of theta. Don't forget the dx term. Eventually, we're going to use the fact that 1 minus sine squared is cosine squared. And that's going to help us get rid of the square root sign. And I think this is the one where this identity might help you at the end to get things back in terms of x. Sine of 2 times an angle is 2 times the sine times the cosine of a single angle. continue here. The derivative here gives me the square root of 5 times the cosine of theta d theta. And the x squared is going to be 5 sine squared. And like I said, the dx is the square root of 5 times the cosine of theta d theta. Just working underneath the radical sign, I factor out the 5. And then replace 1 minus sine squared with cosine squared. So I can rewrite that radical is 5 times cosine squared theta. That gives me another factor of the square root of 5 times the cosine of theta. So I can multiply the two square roots of 5s together and put me a 5 out front. And then we're integrating a cosine squared of theta. That formula looks just like this one, but it has a plus in the middle. So we get theta over 2 plus the sine of 2 theta over 4. But I know I'm going to need to go back to the sine of theta instead of the sine of 2 theta. So I'm going to use this identity here and replace the numerator with 2 sine theta cosine theta. Now this says that x over square root of 5 is the sine of theta. So I can get the cosine of theta. X is the opposite side. The square root of 5 is the hypotenuse. So hypotenuse squared minus leg squared is under here. So that's the 5 minus x squared. And the cosine of that angle then is that radical over the square root of 5. So we have 5 times theta. Oh, what's theta going to be? What can I use for theta? Arc sine of x over radical 5. All that's divided by 2. We cancel that 2. Then I have the sine of theta, which is x over the square root of 5. The cosine of theta is adjacent, the square root of 5 minus x squared over the square root of 5. And all that's over 2. And there's simplifying you can do, but I don't want to. So the benefit of this identity makes it easier for me to simplify. But those take longer. That's why we try to save this kind of trick for the last resort. If it's UDU, try it. If it's a known integral, make sure you recognize it so that you don't waste so much time doing an easier integral than the long way. These take a little bit longer. So with that in mind, I've got a number 11 for you. You write it down over here. We have x divided by x squared minus 25 dx. With the hint that that's all the room I need to do that problem. You can do it longer, but that's all the room I need.
UDU.
It's UDU. It has an x squared on the bottom and x to the first power on top. That's a UDU integral. If you do the partial fractions, you'll get essentially the same result. It'll be an expanded version of the result, but it'll work. It just takes longer. Look for the short steps first. U is x squared minus 25, du is 2x dx. Like I said, it's quick. You notice that the derivative of the bottom is on the top. You can write this as a 1/2 integral 1 over u du. So you get 1/2 times the logarithm of u, and u is x squared minus 5. Okay?
Wait, what, why do you 5 and not 25? Or you-
25. 25. I'm still thinking of that last problem. Thank you. X squared minus 25. 12 is longer. 12, I probably need more room than I've left for. How do I know that? Are you familiar with the integral in problem 12? Have you done enough of those? It's a circular integration by parts. But what you got to be careful of is the 2 and the 5. Try to keep track of your constants. It'll be a circular integration by parts. E's and sines, E's and cosines get you back after the second integration by parts to your original problem. And it doesn't matter which term you call u and which term you call dv. Doesn't matter what's one bit, just as long as you're consistent throughout your steps. integration by parts twice before you give your original integral value. Looks familiar. Looks familiar. Same scheme for your second integration by parts as you did the first. So if you're taking U to be to E, in the second integration parts, take U to be to E. One of them is over here. A certain number of them over here. All right, I'm gonna butt in here so we can get this one done. I'm just gonna take U to be E to the 2x. dv to be the rest. So keep in mind that the 5 and the 2 are gonna show up as halves and 1/5. Or 2 will show up right here as a 2. Right, derivative of the e to a power is itself times the derivative of the exponent. When you integrate, you get the 1/5, and the integral of a sine is a minus cosine. So then over here, we put u times v minus the integral of v times du, minus the integral of v times du. So my u times v is going to be a negative 1/5 e to the 2x cosine of 5x minus the integral of v du. Let me just put it in there the way I just said it, and I'll simplify the next step. So my simplifying step is going to be to take the 2 and the negative 1/5, change the sign and put a positive 2/5 out front. Then I'm going to swap the order of those. So I said I'm going to get a plus 2/5 of the integral of e to the 2x cosine of 5x. So that is very similar to the first integral, and that tells me I've got the other integration by parts to do with the same scheme. Keep u to be e to the 2x and dv to be the rest. So the du is still 2e to the 2x. And here v is going to be a 1/5 sine of 5x. So I'm going to bring this down. That's part of the antiderivative. Put it right here. Cosine, cosine. I'm going to be careful with the 2/5. I'm going to put it outside some brackets. And inside the brackets, we've got our two terms, uv minus the integral v du. So uv is 1/5 e to the 2x sine of 5x minus the integral of v times du. Like that. So I'm going to simplify by putting this back in the order and pulling this 2/5 out as I distribute that 2/5. So I recognize that this guy is the integral that I started with. So I've got that integral over there. I'm just going to call it I for lack of space. Then I've got the negative 1/5 e to the 2x cosine of 5x. Distribute here to get 2/25 e to the 2x sine of 5x. Take this number, that number, put it in front, so that's a 2/5. Distribute that 2/5 gives me a negative 4/25. And then I've got the e to the 2x sine of 5x. In my integral. So I'm just going to call that integral again. So that integral and that integral are both these. Got to get my integral back, so I'm going to take those two integral terms and add them together. I've got a negative 4/5 over here, so I'm going to add it to the opposite side. Think of that as 25/25. Plus 4/25 to give me 29/25 times those integrals to be these two terms. So our last step is to divide by this number, which is the same as multiplying by the reciprocal. So our final answer is that our integral is 25 divided by 29 times negative 1/5 e to the 2x cosine of 5x plus 2/25 e to the 2x sine of 5x plus c. So what did you lose? Did you get everything here, or did you lose something on your steps? Oh, good. Fantastic. Fantastic. Might have time for one more. Life is good. I wonder how long or short this one is. All right, so you're asking yourself, as I write it down, is this a udu integral? Is it a known integral? 2x over x squared plus 6x plus 5. So what keeps this from being a udu integral? This, right? Derivative here is 2x plus 6, and I don't have a 2x plus 6. Right, I could put it in there, but then I've got the other integral that I couldn't take care of. Right, I could add 6, and then take 6 out, do the 2x plus 6 integral as a u du, but then I still have a 6 over that. All right, so it's not perfectly a u du integral. So what is your first inclination then? Partial fractions, because x squared plus 6x plus 5 factors pretty easily. Factors of 5 that add to 6 are 5 and 1. So what you're going to try to do is find 2 fractions that add to that. So that's our plan. We're going to do these as 2 little logarithm integrals. We just need to find a and b. So I'll race you. Put your head down and go as fast as you can. So this is like when you're playing basketball with a little kid and you kind of pretend that you're guarding them. I'm kind of pretending that I'm racing you, knowing full well that I can beat the pants off of you. You beat me? That's okay. I'll take that. I'll take your answer without the plus C. Everybody else get that? Get close to that? Okay, there's more on your little handout. Try them. I'll try to work these out and post the complete solutions on Blackboard.